Do you think that Zoom instruction stuff is going to
It's not putting anything off.
Okay,
I checked this
wonderful.
time. I can't figure out how to get rid of it.
Yeah, but as long as it's not coming to Joe. Well, it's a super duper pleasure to have Katerina Chatziioannou. You can see why it's intimidating to try to pronounce it. Present with us in person. She was actually a classmate in undergraduate school at the University of Athens with Anna Maria Taki, a student of Neil. And then she went to graduate school at the University of Montana, where there's a very strong gravity group. She worked with Nico Younes as her thesis advisor, and Neil Cornish, who works a lot on LIGO data analysis. Then she went to CEDA and CCA, and now she's faculty at Caltech. I heard her this summer at an Aspen Center workshop. I was so impressed with the kind of unification of understanding of the theory and innovations in the theory and in the data analysis. So I thought it would appeal to people, and she graciously was able to come. So welcome. And she's going to be here all week, although maybe spending a lot of her time at CCA, probably. So make an appointment with her if you want to get together.
Yeah, thanks everyone. So yes, I'm gonna be here all day, so feel free to stop by at 9:50, I believe. And the rest of the week I'm gonna be around in the area, so if you want to meet, send me an email. I can stop by. Okay, well, thanks everyone for being here, and thanks for the invitation. It's actually quite nice to finally be able to travel. My last visit to a department in-person seminar was in February 2020, went to Princeton. And this is the first since then, a year and a half. So let's see if I remember how to do this. So I'm going to talk about neutron stars and gravitational waves. So my research focuses on various aspects of gravitational wave astrophysics. And one topic that's close to my heart is neutron stars. Something else I really like working on is testing general relativity. So if that's something that you also find interesting, I'd be happy to talk about it. But today, I will not be talking about testing general relativity. I will be talking mostly about neutron stars. So for those who have been living under a rock since 2015, gravitational wave astrophysics has sort of exploded in the last 6 years, and I'm one of those very lucky people who joined the field slightly before this happened and really has been able to take advantage of all this hard work of the last decades to be able to get to this point and get this wonderful data and analyze them. So this is a plot of everything we had observed up to a certain point in terms of neutron stars and black holes. And we do this both with electromagnetic and with gravitational waves, and that's sort of what's plotted here. But the gravitational wave black holes are the ones in blue at the top. You see they're slightly more massive. This axis here is solar masses. They're slightly more massive on average than the electromagnetic observations of black holes, at least for stellar mass black holes, not talking about supermassive black holes. But we also have a few neutron stars. So you see most of our objects are here, but we also have a few objects down here. These are the orange shade objects. So when you talk about this mass regime and compact objects, there are a lot of things we believe we know. There are a lot of things we do know. Something that is one of the most firm beliefs, at least, and predictions from nuclear theory is that there's a line here at around 3.2 solar masses, which is the maximum possible mass a neutron star can have. If you make reasonable assumptions about how strong the nuclear interactions inside a neutron star can be in order to support it, the conclusion is that it cannot be more heavy than around this point. So anything above this point is a black hole, cannot be a neutron star. Anything below this point, anything below 3.2 solar masses, is traditionally assumed to be a neutron star. For some of these objects, we know they're neutron stars because, especially if you observe them electromagnetically as pulsars, we know they're neutron stars. But generically, you'll see a lot of question marks in this regime. because there is a little bit of an observational evidence for a gap between the electromagnetic neutron stars, electromagnetic black holes, and the gravitational black holes. And we do have a bunch of objects in here with question marks whose origin and whose properties we don't fully understand. So in general, the topic...
That question mark that's up around 20 something, what is that object? There's two question marks around 20.
This one and this one, these are electromagnetic black holes. So I don't know exactly what they correspond to. They're probably some X-ray binary, we're not sure.
So meaning they have a question mark probably because the mass is uncertain, maybe? Or because the identity as a black hole is uncertain?
Probably the origin. So for example, this is the new 3 solar mass object. That's more recent development.
Yeah.
And it's not quite sure exactly if the mass is actually 3 solar masses and where it falls. So some of these are uncertain in that aspect.
Good. But if that object, for instance, that you just pointed at, is it known to have a surface outside the horizon?
No. So there's the main thing we know about this is about 3 point something solar mass measurement, which if correct, the mass measurement is correct, it is most likely a black hole as far as we know, a question of state of neutron stars, but that's not certain that the mass measurement is correct.
I see.
Well,
is it like inclination or something, or is it because it's like based on some Eddington?
Maybe she's gonna talk about this. We could find out.
I'm not going to talk about the electromagnetic black holes. I'm actually going to talk about the ones I'm circling here. Maybe like ignore the yellow guy here. But these are the objects we've observed with gravitational waves. And I'm going to talk about these objects, their properties, and what we know about them.
We'll come back later.
I mean, it's possible because it's a mixed audience that you should explain what you mean about electromagnetic black holes and neutron stars.
Yeah. So the blue ones are the ones we measure with gravitational waves in binaries. That's why they see they come in pair and then they merge. The orange ones down here, again, binaries of neutron stars we observe with gravitational waves. So they come in pairs and merge and give you some object. But we also have electromagnetic observations, definitely of neutron stars. We know because we observe them as pulsars. Sometimes isolated, sometimes in binaries, sometimes even in binaries around other neutron stars. So this is where the orange ones are coming. Sorry, no, this is where the yellow ones are coming from. I can't tell the colors apart very well. And there's also the purple ones, which are the electromagnetic observations of black holes. Electromagnetically, an isolated black hole, you cannot observe it. So it has to be around a companion that actually does the emission. And these are mostly X-ray binaries, where you have a black hole and a companion star. And it's the accretion from the companion to the black hole that actually emits the light, the electromagnetic observation the light you observe. With gravitational waves, we don't need such things. We don't need matter. When it comes to black holes, we can just do everything in vacuum and get just the gravitational wave signal. Okay, so the main thing I will be talking about, is where I was trying to talk about, is these guys here. So these are guys that are between masses 1, 2, 3 solar masses that we observe with gravitational waves. So what can we learn from them, and what are their properties? So the main protagonists are going to be neutron stars, though, as we said, I'm going to, perhaps if I get to that point, also talk a little bit about how we're not 100% sure they're neutron stars. But neutron stars are sort of remarkable objects. When you're thinking about all the possible outcomes at the end of stellar evolution, neutron stars are usually considered to be the second most extreme, because anything more extreme, anything more dense, is a black hole and collapses. So neutron stars are the last kind of object, the last frontier where matter can exist in a stable configuration before collapsing into a black hole. And in these conditions of extreme density in matter, we are actually not certain what the properties are. So there are nice cartoon images for what happens as you go from outside a neutron star to the center, how the density starts increasing, how neutrons start dripping out of the nuclei, how effectively at the center, the very center of neutron stars, with densities much higher than the densities of normal nuclei, everyday nuclei around us, We don't even know what the composition of matter is at that point. Maybe even quarks have started getting decomposed out of nuclei, nucleons, neutrons, and protons. And those conditions are not reproducible anywhere on Earth. Neutron stars are more dense than anything else we know about on Earth. You can see the diagram here in chemical potential and temperature. You can think of it as a proxy for density and temperature. And neutron stars are very dense and very cold. And these are not conditions we can reproduce anywhere in our labs. But the remarkable thing about neutron stars, and one of the things that I feel is maybe underappreciated, is that they are clean systems because they're governed by general relativity. When you're trying to understand their structure, given some nuclear models, that's actually, we know how to do it because we have equations from general relativity. So when nuclear physicists give us a model for what the neutron star structure is, that is expressed through the equation of state, the pressure as a function of density inside a neutron star, then general relativity tells us exactly what this means for the neutron star. So basically it tells us what it means here on the right side, where you have the mass of a neutron star and the radius of a neutron star. So all these lines here that are models from nuclear physicists are in a one-to-one correspondence with lines that are on the right side, on the macroscopic properties that we astronomers can go and observe.
Let's see, spin must make that not an exactly valid statement, or
Sorry?
spin must be an exception. I mean, these are, those mass radius curves must have some thickness because of the range of possible spins.
Yes. So these, I believe when these were computed, they were assuming zero spin. But if you have spin, you can actually compute an equivalent curve and put it on this diagram. We also know how to do this. In reality, we don't know how to solve the equations exactly in that regime. It would have to be some sort of order by order treatment, but you can do the calculation numerically as well. And even if you have some amount of spin, you can put a line on this diagram. That's right.
Stars differentially rotate. Is there any chance that the neutron stars differentially rotate?
I don't think so. I haven't seen any models that would do that. The thing is that there's a couple of things. First of all, neutron stars are most likely in a ground state configuration. They've had, especially the ones seen by LIGO, the ones that are emerging seen by LIGO, have spent millions of years together, and they're in the most stable configuration, where even word they've told spun down, things like that. If you catch a neutron star at the moment it's born, from a supernova explosion or a neutron star merger, and I will get to this, then yes, it could have differential rotation, but then it basically gets rid of that with some complicated angular momentum distribution method that we don't really understand, obviously. So you have to do it numerically. Okay, so the interesting thing about this plot, besides the one-to-one correspondence and the ability to get this from nuclear physics, get this from astrophysics, and really talk to each other. So basically talk together over 18 orders of magnitude from femtometers to kilometers. The other interesting thing you might notice is that on the right-hand side on that plot, the uncertainty of the radius of a neutron star is quite large. We have models going down to 9, 10 kilometers and all the way up to 15, 16 kilometers. That's a 50% uncertainty. In astronomy in general, a 50% uncertainty in the size of something, that's a pretty, I guess, a decent thing. But when it comes to neutron stars, that 50% uncertainty is actually large. It is too large for when you try to understand the phenomena in which neutron stars participate. And that is, obviously a drawback. This uncertainty really ruins your interpretation of some events, but it's also an opportunity, because if the uncertainty on the sizes is important, it means you can use data to actually constrain that. And that's what we're sort of trying to do here with gravitational waves. Try to figure out how big neutron stars are. So where exactly do they fall in this regime? And by extension, we can go backwards and talk to nuclear physicists about which of their models predict neutron stars more accurately.
And the light gray lines are ruled out by observed masses being above 2 solar
Yeah,
masses.
they are ruled out by various constraints, most likely 2 solar mass neutron stars. Yeah, actually in this regime, it looks like all of them are ruled out by 2 solar mass.
I thought there were pulsar measurements.
Go ahead, yeah.
Yeah, but I thought there were pulsar measurements, Scott Rans and others, where they were claimed they detected 2 solar mass.
That's
pulsars
right.
Because it's such a powerful, the existence would tell you a lot about the equation of state.
That's right. So there are two heavy neutron star. There's multiple. The 2 ones that have survived being the highest to date. One is around 2, and one is around 2.1. Both of them are radio measurements of neutron stars in binaries around white dwarfs. One of them has Shapiro time delay measurements, so you can get the mass of the white dwarf and get the mass of the neutron star. The other uses spectroscopic information about the white dwarf, and then to get the mass and get the mass of the neutron star. So these are actually quite useful. And later on, after I describe what gravitational waves can offer, I'm going to show you what the joint constraints can also offer.
Yeah, sorry, just a quick question. You had drawn a line at like 3.2 solar masses earlier, and the top model there is like 2.8. Is that just a spin question, or are there additional classes of models that get you up there?
You can make models go higher. It is harder. It's for sure harder. The problem is that if you make them go higher here, you also need to make them go in larger radii, because it means that the pressure is higher, and that is more challenging to accomplish. You need something really repulsive in the neutron stars to get to these high masses. It is possible. There are nuclear models, but it's not typical. Actually, one of the funny things is, sorry, I'll get to you in a second. If you read papers from 15 years ago from nuclear physicists, that's when the first 1.4, 1.5, 1.6 solar mass neutron stars were observed, and they were saying, oh my God, they're so heavy, what are we going to do with them? And 15 years later, they're all the way down to up to 3. So, whatever we measure, they're going to fit. Yes.
I know there are some protons and electrons in neutron stars, and so is it possible that neutron stars of different masses would have slightly different ratios of those particles, and that the equation of state would then change depending on the mass of the neutron star?
Yeah, so it's a good question, and that's something that you have to be actually worried about when you talk about neutron star mergers, when you do numerical simulations. Neutron stars, the name doesn't mean they're made of neutrons. It means that they're supported by neutron generating pressure. So they have lots of protons and electrons. They have to be charge neutral. So for a neutron star that we observe with LIGO, or we observe like the 2 solar mass ones, these are objects that were born a long time ago and have had time to settle down to equilibrium. The time scale for beta decay is something like 15 minutes, 10-15 minutes. So if you're talking about a neutron star that's older than this, it's probably an equilibrium configuration with a stable composition. But if you talk about neutron star mergers, then when you actually go to model them, you have to take into account changes in the composition, because when they're colliding in less than 100 milliseconds, you have to take this into account. So when you try to do simulations, if I give you a pressure versus density, that's not good enough for you. I also need to tell you how it changes composition. Okay, so this is the general picture with neutron stars. And I'm going to talk a little bit about gravitational waves. I don't know how familiar you are with gravitational waves and the remarkable progress in the last 5 years. But the first gravitational wave detected, and the vast majority of signals we've seen today, and also showing from my first slide, is from black holes. And those have signals like this. This is 5914, the most famous one, because it was the first one, front page of the New York Times and everything. And it looks kind of like that. It's kind of short, the increase in amplitude, the increase in frequency, the 2 black holes collide. Compared to this, and all these different binary black hole signals, this is Tidal 170817, which is a binary neutron star signal, the first we observed. And compared to all these, this is what it looks like. We have to wait for a while because the neutron star masses are lower, they emit less energy in gravitational waves as they orbit around each other, so it takes longer to merge. I'm not going to play the whole thing because it lasts for like 2 minutes. But you have to be patient when you're observing neutron stars. It's not black holes where you blink it and you missed it, lasting milliseconds, tens of milliseconds, or up to a second. Neutron stars take a while.
Was the neutron star found in the same kind of template search as the black holes? Is it a coherent template search that can find the neutron stars and the black holes, or is it really done by a different pipeline?
It's the exact same pipeline. And it has templates down to 1 solar mass and up to like 400 solar masses.
I see.
It's the same.
And the pre-merger it doesn't really matter that much whether it's a neutron star or a black hole, I guess.
That's right. That's right. And I'm going to talk about it in the next slide. But in the meantime, what I want to tell you is that it's not all just waiting for this thing to go around each other. If you are patient enough and wait for those 2 minutes, at the end of the neutron star merger is where the really exciting stuff happens. And that's a numerical simulation. You cannot really understand merging neutron stars analytically. You have to do it in numerical simulations. So here are my 2 neutron stars getting close together, the gravitational wave signal here. And once they get really close together, you'll see that they start ripping each other apart. They start tidally interacting. Here they collide, they emit matter all over the place, a complete mess. You see how complicated the signal looks like here, and you have a final remnant here, which is a very young neutron star, where things like composition really matter because it does not have some steady state. And then eventually it could collapse into a black hole. So from our perspective, from a gravitational wave signal perspective, when we try to measure it, we measure a signal like this. This is the amplitude, the signal of an amplitude, let's say, as a function of frequency. And the U-shaped lines, the blue and the gray, are detector sensitivity. So the further down those lines are, the better, because the more sensitive you are. The blue is the sensitivity back in 2017 when we observed GW170817. The gray is the design sensitivity. I hope to achieve in the 04 run starting sometime in 2022, hopefully, pandemic permitting. But the signals in this plot are those lines that go down. The amplitude decreases as a function of frequency. So these are the signal from 2 neutron stars. The amplitude of the signal is a function of frequency. And there are distinct phases in such a signal. Most of the time is spent in what we would call an in-spiral. This is where the neutron stars are far apart. Like Hogg said, it doesn't matter that they're neutron stars. It might as well be black holes because they're so far apart from each other and they slowly emit their energy in gravitational waves. Eventually, they would get so close together in the late in-spiral, where they're going to start tidal interacting each other. They're no longer going to be spheres, but they're going to start stretching each other. And eventually, there's no turning back. They have to collide and form a final object. The different colors you see here in those lines is what we're interested in. This is the signal as emitted from different neutron star equations of state, so different models about the neutron star structure. And early on, when the neutron stars are very far apart, the internal structure doesn't matter. This is one of the basic principles of general relativity. When they're far apart, the internal structure doesn't matter to gravity. But when they get close together, that's when the different lines give you different predictions, different colors give you different predictions, the different equations of state give you different predictions. So if you go and measure that signal, that's when you can get information about the equation of state. Yes?
How many parameters do you have in your models for simulating these mergers?
For simulating these mergers. So the parameters that describe the system, not the parameters that describe the signal.
Yeah. No, the parameters that describe the signal.
As seen by Earth or as seen outside from Earth?
Yeah, outside from Earth.
Outside from Earth, you have 2 masses, 6 spins, because you have magnitude and direction, and also the equation of state.
And from your perspective, the equation of state is like something in a lookup table. It's like you don't really have knobs in your equation of state. The equation of state is something that's given to you by like a nuclear physics approximation scheme or something.
When you have to do a simulation, you actually have to do exactly that. But when you try to interpret data, you basically have to solve the backwards problem. And there you have to be a little bit smarter than this. And I'm gonna get to this.
So related, so on your earlier slide, you showed basically almost like 15 or 20 different models for the equation of state. And here there are three, right? Three colors. Are these like kind of the extremes, like the stiffest to the kind of softest equation of state? That
Yeah,
shown
more or
here?
less. Like there's actually a fourth dashed line here. It's dashed because it's
yeah.
ruled out.
Okay.
So yeah. But that give you an
this-
idea.
So where the noise blows up, right? That's what you want to actually measure. That's what becomes interesting.
So that is the interesting thing. You see that the effect of the equation of state is more prominent here, but here you're under the noise. The effect is more subtle here, but here you're above the noise. So there's a little bit of trade-off. And as the detectors get better, we're gonna get more and more information. We're gonna get qualitatively new information because you can have access to this part of the signal.
But I have my spider sense about these last bits is that there's a lot of kind of chaotic turbulence type things going on at the end. So my guess is those waveforms are more confidently predicted also as you are closer, as you were earlier.
That is correct. And when we get to the post-merger, I'll try to convince you that you can still get something out of them. There was one more question? Yeah.
Sorry, just a question about the detections. For it to be considered a successful detection, do you have to have both the late in spiral and the post-merger? Or do you
No,
use
the
just
detections
late in
come from
spiral?
here.
Okay.
This is where all the signal is.
Got it.
Was one more question?
Yeah, so will the shape of the signal you predicted depend on the initial condition of the simulation, or because I mean it's highly non-specific, you change the event, will the shape of the signal?
So this is plotted as a function of frequency.
Oh,
So when it reaches that frequency, it will have this shape. The thing that does affect a little bit the signal is whether you start by accident, start with eccentricity or not. You're trying to start with a circular binary, but you can see some wiggles here. This is probably residual eccentricity in the simulations. That's hard to get rid of. Okay, so I'm going to talk about those three stages and describe a little bit more what they look like, what we can learn from them. And the easiest one, and frankly, the perhaps less exciting about equation of state is in the spiral. But this is important because this is where we actually measure things like masses and spins, and this is also how we detect them, as we just mentioned, because that's where most of the signal is. So we saw the nice wiggles from binary black holes. Compared to that, this is what the spiral of neutron stars looks like. There's actually two waveforms plotted on top of each other. There's the blue and the orange. And the reason we don't usually plot those because they're so many cycles, they're so long, it just looks like a blob. But if you observe,
Are there like unresolved vertical things or?
sorry?
You said so many things. Oh, but I see, this is really all there is. It's not like there's an unresolved underlying.
Yeah.
It looked like I thought I saw little crinkles in the bottom of the orange one. And so I thought maybe this was like a fused, very, very high.
No,
frequency.
this is mostly for dramatic effect, just to show you that you have two neutron stars that start around 400 kilometers apart when we start observing them. And over the next about 10,000 cycles, and at design sensitivity, not today, in the future, hopefully lasting for 10 minutes, they go from far apart to losing their energy in gravitational waves and getting close to
So
merger.
in fact, there is an enormous number of cycles and
Yep.
they are merging and it's, okay, got it.
So this is 10,000 cycles plotted, and of course you can't see anything.
Sorry, so is today's resolution large enough to tell the difference between neutron star merger or black hole merger, just based on the LIGO?
Yeah, actually, there's no difference here. This is the stage where the two neutron stars might as well be black holes of the same mass. There is no difference in the signal because they're far apart. There are no tidal effects separating them. So that is basically like a point particle. You can treat it like a point particle. And modulo some ideas about resonant excitations in neutron stars, that maybe you can hit them as you go around some point, the orbital frequency hits some sort of resonant frequency in the neutron star. Modular ideas like that's basically might as well be black holes.
So what about, I mean, the final part,
Yeah, so this is I'm talking about the in-spiral here. We'll get to the final part in 2 slides.
And during this period, can you measure the initial spins or some combinations of the spins?
During this period, you mostly measure the masses, but you might be able to get some information about the spins. The reason it's so hard to get information about the spins is that actually there's a pretty nasty correlation between the masses and the spins. So here is GW 170817, mass of one neutron star, mass of the other neutron star. And the blue and the red is under 2 assumptions about the spin of the neutron star. Either the spin is small, which is sort of inspired by galactic neutron star binary observations, or you allow it to be large. And this is the dimensional spin parameter that you define in general relativity. If you prefer talking about period of like a pulsar, rotational period of a pulsar, this is the conversion. So a 1 millisecond pulsar would have a spin of 0.4 in those dimensionless units. So this is sort of what we measure. The masses are consistent with what we've seen in the galaxy, around 1.3, 1.4, 1.5 solar masses. We measure amazingly well a parameter called the chirp mass. The 2-dimensional plot, it looks like a line. It's actually 2-dimensional, but we measure this parameter, this direction extremely well. It's called the chirp mass. We measure the other dimension significantly less well. This would be something like the mass ratio, the ratio of the 2 masses of the system. We don't measure it nearly as well. And the problem is that this is actually quite correlated with the spins. So if you want to assume that the spins are small, like pulsars in the galaxy, then you get a better measurement of the masses. But if you allow the spins to be large, you get a much larger uncertainty. And if the spin, your spin prior assumptions matter so much, it means that you cannot really measure the spins all that well either, because of all those nasty correlations.
So this is the effective spin, right? This is kind of the effective spin of the system, right?
What is plotted here is the spin along the angular momentum of the individual systems, the individual neutron stars.
And a typical neutron star in the galaxy, we think is about what, a 1 second period or a
Some of them can have, so I should probably
the
clarify my
millisecond
statement.
pulsars are rare, right? Most of them are not
Yeah.
spinning that
To
fast.
clarify my statement, the neutron star binaries we see, binaries are the neutron star, we know of like 20 or so,
Yeah.
pure. If you take them, assume they come from whatever separation they are down to gravitational wave separation and continue spinning down, when they reach that point, they will have spin less than 0.05.
Got it.
This is where the 0.05 number comes from. Okay. So there was this question, okay, all this nice and everything, but eventually the neutron stars will get close together, and that is where the excitement happens about equation of state. So let's talk about this. So to understand this, I'm going to show you 2 simulations. These are numerical simulations of 2 neutron stars orbiting around each other and merging, where everything is the same in those 4 neutron stars, apart from the equation of state. They're just 2 different equations of state left and right. You already see the difference. These are bigger, these are smaller. So let's start playing the simulation. And you can already see the difference. These are going faster. The bigger they are, the more they tidally distort each other. You see these are already not spheres anymore and merging, while these are still happily orbiting around each other. So the bigger they are, the more energy they emit. So the faster this whole process is going. Eventually, these will also merge, of course. There's nothing else they can do. But it just takes longer for this whole process to happen. Because these lose energy faster, these lose energy less fast. In terms of the signal, in terms of actually modeling this process, this is the standard theory of tidal interactions. Think Earth and Moon tidal interactions. If you have a spherical object, you put it in an external tidal field, what it will do is it will be stretched. It will grow a quadrupole moment. In this case, you actually have 2 of those. So each of them stretches the other neutron star. And you get an equation of this form, where you have the quadrupole moment raised in a star is proportional to the tidal field created by its companion. And this constant here, this little constant, is everything we care about. That's called the tidal deformability. And it basically tells you how easy or how difficult it is to deform a star. If this is large, then it means the star is more deformable. If this is small, it means it's less deformable. And that's what we measure. This is where the information comes from. Because that affects the inspiral, and also it depends on the equation of state. If a neutron star is large, it's more deformable, so this is larger. If the neutron star is small, it's more compact, it's less deformable, so this number is smaller.
I feel like the mass ratio must come in here in the sense that if you have two equal mass versus a big mass difference, I feel like the combined tidal effect should be a function of that.
Yep. The combined tidal effect is given by this equation that has the masses and the tides. So this is what we actually measure. So it's not as clean of a measurement as you were hoping. We don't directly get information about the equation of state. We measure a big nasty parameter that includes everything. But this is what the signals look like. This is a signal in the time domain as a function of time, and this is the same signal in the frequency domain as a function of frequency, plotted for different values of this parameter. So 0 means no deformation. This means black holes. Black holes, we believe, do not get deformed as they approach each other. And as this value increases, you have more compact neutron stars and less compact neutron stars. So if you look, for example, in the frequency domain, it might be more clear. If with your eyes you follow the peaks of the waveform, you see that it goes from the blue to the magenta to the green. So the less compact a neutron star is, so the bigger a neutron star is, the faster again it emits energy. So the faster this in-spiral progresses. So the earlier it merges, if you look at it in terms of time, the blue merges before the pink or the green.
Can I ask a very naive question from a non-astrophysicist?
Sure.
Is there any possibility of there being an atmosphere or any sort of other gravitationally bound stuff around a neutron star?
So the thing is that dynamically, at that stage when they're really close together, dynamically the only thing that matters is the central part of the neutron star, because this is where all the mass is. So things like anything around the neutron star, the main thing that could have contribute additional energy around the neutron star would be something like a magnetic field. And even then, you need extremely high magnetic fields to compete with the gravitational attraction between the neutron stars. So even if you have a little bit of mass around it, unless it's comparable to one solar mass, it's not going to dynamically affect anything.
So it won't slow down or speed up or slow down the inspiral in any way that could be confused with changing the equation of state inside the neutron star?
No, so for magnetic fields, you need something of the order of 10 to the 18 to make any difference. There are ideas, more exotic ideas about boson clouds around neutron stars and things like that that could provide additional friction if they have enough energy. But in the more standard astrophysical picture, when the only thing you can have is a magnetic field, then they probably cannot affect the inspiral unless there's an exceptionally large magnetic fields.
And things like planetary systems or rings or stuff just couldn't matter just because it's not enough mass.
Yeah, and also you'd have to somehow figure out a way that a ring around a neutron star survived for millions of years while the neutron stars got close together and survived when you have two neutron stars 10 kilometers apart. There was another question, I think? I think I saw a hand. Okay, never mind. No. Okay, so this is what we're trying to measure. This is the main thing we're trying to measure. And this is what happened for 170817 when we tried to do this measurement. So here is the tidal parameter of one neutron star, tidal parameter of the other neutron star. And there are some different lines here, different colors, giving you different posteriors under slightly different assumptions for how you do the analysis. But the main picture, the main thing to remember from 170817 is that it put upper limits on things. So in the large lambda regime is when you have less compact neutron stars, bigger neutron stars. And it seems to that the data basically pull us down in this regime, in the low regime. So they point to smaller tidal interactions in the system, smaller radii in the neutron stars, more compact neutron stars rather than bigger neutron stars. In terms of, if you want numbers, I'm going to show you a little bit later as well. The upper limit on the radius is about 13 kilometers coming from the gravitational waves. If they were larger than this, we would have seen larger tidal interactions than we're actually seeing in the data. Yes?
How do you produce these posterior distributions? Do you have a pre-computed grid of models, or do you have to use an emulator to?
Our
do some
models
sort
are
of-
actually fast enough that you can do something like stochastic sampling.
Oh, wow, okay.
And also on top of this, we have very good, well-defined models for detector response and noise in the detector and things like that. But a model like the ones I showed here, that takes milliseconds to produce. So you can do it in the fly. We're quite lucky in that aspect. Lucky, I say lucky, it's decades of work from people, is what I mean. Yes,
Are you only sensitive to quadruple tidal disruptions also?
yes. Today, the leading order effect is this number, and that's the quadruple part of the tidal interaction. You can go to higher order, and the computation has been done to higher order, but unless you have a more sensitive detector, you don't see the signal.
So from the electromagnetic radiation for the kilonova, right, being part of the kilonova, where people using various models could constrain what the products were that were produced, all process elements, right? There were also, I thought, constraints on the equation of state,
Yes.
right? And is that consistent with the gravitational only constraints?
I'm gonna go straight to that because, why not, since the question is here. There you go. It's a slide I want to show. So we have, of course, electromagnetic information from GW 170817. And here is the measurement of the tidal parameter. The blue is only from the gravitational wave. And as I was saying, what it does, it pushes you down, puts an upper limit. If you look at the interpretation of the electromagnetic signal with the caveat, with all sorts of caveats about systematics here, what it does, it pushes you in the other direction. The reason is that in order to produce the kilonova, the leading interpretation for where the ejecta comes from is that there's a large component of it coming from a disk around the central object. So in order to form a disk around after the merger, you need the collision to not be too violent and result in an object that immediately collapses into a black hole and swallows everything. So in order to do that, you need things to not be too compact and collapse immediately into black holes. You need them to be more extended and leave disks behind. That's why this pushes you up.
When you use the notation lambda tilde instead of lambda 1 and lambda 2,
It's a combination of everything together with masses and tides. This is the thing we measure.
It was the thing with the 16/13ths, right?
Yeah.
And the m's to the 12.
And that, for reference, is one of the more simple expressions we have. You should see some of the fractions that go into these equations that have 15 digits in the numerator and 16 in the denominator.
But that calculation is basically pure GR, right? So it's actually a very solid calculation.
Yeah, this is pure GR.
Yeah.
This is pure, you have an object, it grows a quadrupole moment, that quadrupole moment emits gravitational waves.
Yeah.
So, yeah.
And to translate bounds on lambda into a statement about the equation of state, that
Requires what I'm going to talk about next.
Can I ask one thing before you go on?
Yes.
I mean, wouldn't the equation of state also determine, so you can have tidal locking, right, over many orbits because of tidal effects?
Right.
Equation of state must play into that. And if you change the spin, then you change the gravitational wave signal.
You actually don't have tidal locking. So neutron stars in those binaries are not tidally locked. The viscosity cannot do that.
Okay. So
What happens is, actually I can use the board. What happens if you have a very fast response of the object.
maybe I'll turn off the light for the sake of our.
What happens is if you have the binary and they look like this, and they're going around each other, when they rotate by pi/2, they're going to look like this. The bulge is going to facing each other. It face each other. I can't really draw very well. They face each other. But the bulge has actually moved. This point in the star is here. They're not tidally locked.
But I guess I didn't mean they would become tidally locked. I just meant that there should be some effect on the spin from the tides on these neutron stars, and that must be affected by the equation of state. And if you change the spin, you would change the gravitational wave signal just a little bit.
That's right. That is a higher order
It's higher
effect
order, okay.
to what I'm describing here, especially if the neutron star spins is like 0.05, when we discussed about having low spins. The effect is going to be very small and higher order. Thanks.
See, but if they're spinning fast, they'll just pass through a co-rotation without even being locked. They'll just pass through it.
Yeah, if they're spinning fast, actually all sort of exciting things can happen.
Yeah.
And that would be nice if we actually get something like that. Because they can also pass through resonances and things like that.
Okay.
Okay, so there was the question, you measured this lambda measurement, and what does it mean about the equation of state? So here's an analysis about this. Here is the mass and the radius inside a neutron star. And you start from a prior, which is the black. The black, two lines of the same color show you the 90% credible region. The black being the prior, where you start from, and then you start adding more and more data, and you constrain things more. So to actually answer the question about how you go from lambda to the equation of state, you need to have some model for the equation of state that you compare against all your data. There was a question earlier about how tied you are to nuclear models. And ideally, not at all. You don't want a model that is based on some specific set of nuclear calculations. So what happens is people have devised all sorts of parametric models for the equation of state based on polytropes and things like that. This particular study is actually based on a non-parametric model based on a Gaussian process. And as I guess my grad student who did this analysis pointed out, the more parameters something has, like a Gaussian process, the more non-parametric we call it. But we're gonna call it non-parametric. But this is based on a Gaussian process to generate potential pressure density lines that you then compare against the data. And that can create all sorts of different phenomenology that maybe the nuclear physicists have predicted, maybe they haven't, but if we detect it, we can actually give them some useful input. So those lines here use different data. We discussed already that we have heavy pulsar measurements. This is the light blue. These are those pulsars up here that have large masses, 2.1 solar masses. So what do these do? They basically push you from the black to the light blue. Because if you have something like a 2 solar mass object down to a radius of 10 kilometers, that means that you need a lot of pressure in order to support it against collapse, which means that the pressure is high, which means that the radius is high. So it pushes you up, pushes you in this direction. The radius cannot be too small, otherwise you can't support such heavy systems. The gravitational waves have the opposite effect. They take you from the blue to the green, the light blue, I guess, to the green. Remember, we talked about how we didn't see tidal effects in the system, so we put an upper limit on the tidal parameter, which means an upper limit on the radius. So that brings you down. And I also have one more measurement here, which is X-ray data about neutron star sizes, and those give you some estimate of the radius that have the opposite effect. They push you up. So that is sort of the best of both worlds. You have constraints from different sides pushing in different directions, which means if you combine them, you get the stronger constraints. And then, of course, you hope that they don't end up in a situation where they disagree with each other and push too much. We're not yet in this regime, but ask me again in a few years if we'll ever get to this regime. Yes?
I'm wondering about your prior. Is that just from theory, what we know that neutron stars have to be between? And then how are some of the bounds going outside the prior?
Yeah, so these are 90%.
Oh,
so
90%.
they have tails.
Okay.
It's actually really hard to plot. This is, if you have any ideas how to actually do it, I don't know how to correctly, very nicely plot functions and credible intervals of functions. Sure. So you have to pick something and then truncate it at a certain point.
And it's just the theoretical.
So this is what comes from the Gaussian process, and we sort of restricted it in here because we knew that this is where the data is. If you get a measurement out here, we'll probably extend it in this direction just to see what happens. Yes.
There are all kinds of scenarios that claim that at the core of the neutron star, it's not nuclear matter, but rather quark matter.
Yes.
Are these observations can shed any light on this issue, whether it's really there?
Yeah, so this, let's see, I have some slides about this later. Actually, do you mind putting a little semicolon on this and get back to it in a few slides? The answer is we can test for it, but we don't have enough evidence yet, but we can in the future, and I will explain how in the future we can do this. Okay, so what time is it?
5:03, but don't feel
Oh,
pressed.
wow.
At least
So-
I think I'm speaking for everybody that we're having a
Let's-
great time.
Let's see, I'm gonna skip a few things because I really want to talk about post-mergers. Because that's also where we can talk a little bit more about quark matter in neutron stars. So I hope you all agree there's a lot of exciting stuff happening here. So feel free to keep asking questions and come find me later. But I also want to talk a little bit about post-merger, because even though it's buried inside the noise, I think it's exciting. And I also promised to answer some previous questions here, so I have to actually follow up on this. Okay, so this is the post-merger where the two neutron stars collide. And roughly speaking, there are three potential outcomes when you have two neutron stars colliding. So here's two neutron stars coming in, and there are three outcomes. The first is that whatever you have directly collapses into a black hole. It's so massive, it cannot be supported against collapse by anything. It collapses into a black hole and gives you a ring down. The final black hole rings down the same way the final black hole and the final black hole merger rings down. And that signal, if you do the calculations, are around 6,000 hertz, which is absolutely prohibitive for us. 6,000 hertz is way too high for our detectors. We don't even calibrate the detectors up to this frequency. We collect data, but they're not even calibrated. So we cannot use them. On the opposite extreme, you have this scenario where you have something that survives as a neutron star. They collide, they fuse together and form a neutron star. And that neutron star could survive for a while, maybe minutes, maybe indefinitely. We don't fully know, because it depends on a lot of things like magnetic fields that can dissipate spin in the system. But in between is perhaps the most exciting case when it comes to gravitational waves, and also what we actually think happened to GW 170817, where you have a neutron star that forms for a little bit, survives for a short amount of time, and then collapses into a black hole. In this case, you have a short duration signal for as long as a neutron star lives that comes at around 2,000 to 4,000 hertz, which is still high. As we said, the post-merger is at high frequencies that's in the noise, but we can work with 2,000 hertz. It's not completely prohibitive like 6,000 hertz. So in that case, remember I talked about those beautiful models that came after decades of work from people. None of this works here. When you have two neutron stars colliding, you have to actually bite the bullet and simulate this numerically, because there's nothing else you can really do. And what happens, what simulations tell us, is that you have a short duration signal at high frequency. So this is the frequency time decomposition of the signal. When the colors are darker, this means where the power of the signal is. In the time domain is up here, and the frequency domain is here. And we discussed it earlier about post-merger. There's a lot of bumps and wiggles, and there's a lot of motion in the stars that we don't fully understand. What supports this neutron star from collapse is differential rotation mostly, and some temperature effects. And those systems collapse when they have lost their differential rotation and are down to solid body rotation. How exactly they lose this differential rotation and how this distribution of angular momentum happens in the system is not fully clear, and depends on a lot of physics, that some of which is not correctly and fully modeled in the simulations. But besides all this seemingly chaotic situation, there are some robust features in the signal, and the robust feature in the signal where different simulations, different codes from different people, different physics seem to agree on, that most of the power comes in one semi-constant main frequency component. So the spectrum has a peak, basically. And that peak is interesting. If I pull back the simulations from earlier, if you remember, I have the small neutron stars and the big neutron stars, and now they're in the post-merger stage. And you see that they basically have two blobs orbiting around each other. They fuse, so they're sort of rotating. And this rotates faster than this. So the more compact is, the more violent the collision is, the more high the density of the remnant is, the higher this frequency is going to be. And that is the connection to the equation of state. So basically what exactly this happens depends on the equation of state. Because it basically depends on the density of the remnant. Okay. So
this is before it forms a black hole.
this is before it forms a black hole. It might or it might not form a black hole. We don't know.
Okay.
Sometimes the simulations can't even track it for long enough to know if it actually collapsed or not. Because it can, if it happens after half a second, it's hard to track it for that long.
But what else could it do? I mean, if it's got most of the mass of two neutron stars in it?
So if the mass, after it loses differential rotation, it's still spinning. So maybe the spin can support it for a little bit. But it can keep, if it has a large magnetic field, it will start losing that spin. And eventually will collapse from this. It's uncertain exactly where it falls in this range of possibilities. Okay, so we tried to do this for GW 170817. I mean, we did it, but we didn't detect a signal. It was just buried in the noise. So these are upper limits on the energy density of the signal as a function of frequency. And these are example signals for what it could have been based on simulations. So take them with a grain of salt about the uncertainties in the simulations. But those are sort of the predictions for where it could be. So we're not quite there. The fact that we didn't see the signal doesn't mean that it's not there. We were about a factor of 3 away from seeing it. But it's not too bad because eventually we will be able to. So here's some simulated data. The black is the signal. See, it's a beautiful peak here. And the dashed shows you the detector sensitivity. And I'm going to start playing this animation. So what happens in each still of the animation, the noise in the dashed line goes down. So you get a more and more sensitive detector. When the sensitivity of the detector increases, the signal comes out of the noise and you start recovering it. So first, the dashed lines are how you recover it in your analysis. You first recover this bit, which is a merger at lower frequencies, around 1,000 hertz. But eventually, you also start grabbing this part, which is the main frequency component of the signal that tells you something about the equation of state. And you can sort of do it with upcoming detectors, something like 2 to 3 times better. A detector that's about 3 times better than LIGO can do it, can observe it. And if something that's 3 times better than the design sensitivity of your instrument sounds very scary, I should actually tell you that there are already plans to do it. So the upcoming observing round will be design sensitivity. And there are already plans funded to go one step beyond and reach this sort of level of sensitivity in what we call 05, the 5th observing round. So it's not hopeless. We can get there instrument-wise, and we're also working to get there analysis-wise, because these are more complicated signals to analyze. Okay, so I also then want to talk a little bit about quark matter. There was this question about what happens if inside the neutron stars, the core is not made of neutrons anymore, but you also start having something like a strong phase transition to deconfined quarks, something like that. So if nuclear physicists think that this happens, nuclear physicists, I should say, are certain that this happens in some density range. If you go to something like 40 times the nuclear saturation density, which is saturation density is the density in nuclei, then they will tell you that their simulations say that there's deconfined quark matter. The problem is that neutron stars don't reach those densities. They reach like 5-6 times saturation. So at some point, this phase transition happens. Whether it happens inside neutron stars or at densities that are not relevant for neutron stars, we don't know. But we can go and look. So if it happens at low densities, such that our normal 1.4 solar mass neutron stars are affected, we can observe it with all the measurements, the tidal interaction measurements I showed you. Currently, there's no such evidence that something like that happens. We have constraints on the parameter space and things like that. But what I think is more promising is what happens if you consider the post-merger. Because let me show you, again, the nice simulations. I really like them, as you can probably tell. So these are two neutron stars. The colors show you the density. So the darker that red, the higher the density. And you see the density, they reach quite high densities. But once they collide, they reach even higher densities. So that gives you access to even higher densities than normally possible if you detect such a signal. And maybe the phase transition hasn't happened in the 1.4 solar mass neutron stars, because we're sort of getting evidence that it hasn't happened in the normal neutron stars. Maybe it happens in this guy at the very heart of the remnant that you measure after the merger. I'll skip a couple of things and just show you this result, which is from a recent analysis. Again, we haven't seen this is simulated data, but trying to convince you we can do it in the future, where you have, let's look at this. This is a signal in gray is a simulated signal. It's a function of frequency. And you analyze it. This is the in spiral. You recover it extremely well, but you can also recover the post-merger. And then you can go and compare them. You can look at things like this, where you can compare a quantity you measure from the final neutron star that's formed after the collision, the frequency of the peak, and you can compare it against what you measure from the in spiral before the neutron stars have merged, this quantity. If you have a hadronic equation, you have an expectation for what happens between the two. They should have a relation shown by this shaded region. But if you actually have a phase transition, you might not follow this picture. You might find a inconsistency between the in spiral and the post-merger. And that inconsistency would be a smoking gun for some additional exotic physics happening. I don't know if I would call it exotic. Additional physics beyond a hadronic equation of state. So I think this is one of the most promising things and why I really want to get to talk about the post-merger, because it allows us to probe higher densities and more complicated conditions that two nice neutron stars that are boring have been sitting there for millions of years and have settled down to a steady state. But it also allows you to look into what happens at more dynamical forms of matter that has just collided and neutron stars that have just been born. So this was my answer to the quark matter question. We don't have any evidence yet, but we could do it in the future. And there are some nice ideas for how to do it.
You're not saying that the equation of state is known for quark matter, just that it'll be different. Isn't that right? Or are some people confident that they could make a prediction about the quark matter equation?
No, so what we're trying to do is figure out the transition. There's a transition between the two.
So the evidence is not lying on the curve, but it's not, I just was surprised if there are people who think that you can predict what that would be.
There are, of course there are.
Oh, that's true. I'm sorry, I just
Yeah,
But what we're more phenomenologically, what we're trying to understand, if this is pressure, this is density. If you have a line like this, a nice line like this, or you have some sort of line like this. This is what you're trying to do.
I mean, there are generic things because it should make the whole thing softer in general if you can go through a phase transition.
It will make the density larger. You'll be contracted more, and because if you start making new species, you lose pressure, you contract, you increase the density.
Related to Matt's question about like what else could there be, you're talking about gravitational wave observations post-merger, but of course there's electromagnetic observations post-merger, and even if it falls into a black hole, we might expect to see a late time accretion signature or maybe even some kind of dynamical system. Are people monitoring the aftermath of these things well in electromagnetically?
Oh, how aftermath are you talking about?
I'll take any time scale from seconds to years. I mean, things could even appear on long time scales.
Yeah, they're still observing GW17.
They are, good.
Yeah,
Good.
not in all the bands, but they can still see it in some.
Okay, good. Because there could easily be an accretion event that later, which would tell us a lot about.
Yeah, there's actually some suggestion of a rebrightening, which has been interpreting as the ejecta colliding with interstellar material.
Yes.
But that is less. There's some debate in the literature because it's based on one data point which slightly goes higher than the rest. So let's see if you get more data points that go higher. Yeah, but it's possible. But they're observing them.
And the kilonova models that you talked about, you said there's constraints from kilonova. Is that like material that is truly unbound from the system, that's truly thrown off of the final system?
The constraints I discussed here are basically the conditions to make unbound material. Like you need a disk that will eject all that material. The problem is once you get to the point of a disk and unbinding material, the timescales are large and you can no longer track this with a kind of simulations that do this.
Yes.
So you need to basically run those simulations, take initial conditions and take them to different codes, and then hope that all this is actually accurate.
Yeah.
Okay, it's 3:10. Let's see. Do people want one slide on neutron star black holes, or should we stop here if you have to run? I think there's like a faculty meeting, I was told. You have to run too.
Well, the faculty is here.
I'm not a faculty.
So you want one slide on neutron star black holes? Let's do this.
Let's do it.
Yeah, that's good.
So neutron star black holes are kind of sometimes a forgotten child, but they happen. We actually observed 2 of those for the first time a few months ago. So what happens here? You have a neutron star and a black hole, and there are basically 2 things that can happen. Here's the gravitational wave signal as a function of time, and you have a red signal and a blue signal. So what's the difference? Is there the 2 possibilities? The blue signal is what happens when the neutron star is so big that the black hole is so big that the neutron star just falls into the black hole. Here's just from a simulation that shows you the apparent horizon of the black hole and the neutron star just falling in. If it just falls in, then the signal kind of looks like a binary black hole. You can't really tell anything apart. On the opposite extreme, the neutron star could be completely torn apart by the black hole. As it's coming in, it gets completely tidally disrupted, forms a disk around the black hole, and the black hole starts accreting. And then what happens is actually quite funny. You have a neutron star orbiting around a black hole, and then you don't have a neutron star anymore because it has been disrupted. So the signal basically shuts off. This is what the red case, where you're having those nice wiggles, orbiting, and then just shuts off. There are, of course, in-between cases and everything, but these are the main phenomenology of those systems, that you basically have a neutron star coming in. At some point, it will be disrupted by the black hole. At some point, it will fall into the black hole. So which of these happens first completely changes the phenomenology of your signal. And there have been a few observations that we believe are neutron star black hole systems. Here are masses M1 and M2. And M1, look at the masses 5, 10, 15, 20. These are black holes. These are very heavy. They're up here. But there are those systems here that are low masses, 1 solar mass, 1.7 solar masses. These are probably neutron stars, though we're not completely sure. We didn't see any tidal signature from those. So we need some sort of external information. If you tell me you're sure that a 1.7 solar mass object is a neutron star, cannot ever possibly be a black hole, then that's a neutron star. But the gravitational wave signal will not tell you the answer. And every once in a while you get, once in all our systems, you get this weirdo up here. This object is 2.6 solar masses. And we actually don't know. We don't really know. This is either the lightest black hole we've ever observed at 2.6 solar masses, or the heaviest neutron star we've ever observed at 2.6 solar masses. but we don't know. So you need some at some point, the gravitational wave signal, and that's a bit of a downer actually, cannot give you all the information. So you need to get some external information, like compare it. These are estimates for what the maximum mass of neutron stars is, different estimates. So at some point, you need to compare against external information about what neutron stars could look like. And this is where I think there could be a lot of more discussion between different communities, because if I talk to an astronomer, a 1.8 solar mass object, they will tell me, what are you talking about? It's a neutron star. But then if you talk to people thinking about things like primordial black holes, they get excited about objects like this when we cannot prove that they're neutron stars. Because they can say, well, maybe you can astrophysically make a black hole at 1 solar mass, but what if it has a different kind of primordial origin? So yeah, this is my pitch to you to think about whether you want to object to our claim that a 1.2 solar mass object has to be a neutron star even if we cannot prove it definitively.
I mean, in your opening slide, you emphasize that the neutron stars are all below 3.2, but actually it's kind of just as impressive that almost all the black holes are above 3.2. Like, it really does seem like the universe does split at some mass somewhere between 2 and 4, and almost everything below is a neutron star and almost everything above is a black hole. But I don't know how confident I don't know whether a lot of those things should have question marks in them or whether.
Yeah, so everything you observe as a pulsar is a neutron star. But the question is there anything, and we have not seen electromagnetically a dark object with a companion that, it seems to have 1.5 solar mass, the 1.5 solar masses. But with gravitational waves, we get all those systems where there's no real proof that they are neutron stars. And it depends a little bit on how ambitious you want to be and whether you want to consider this possibility and what happens there. But even if you don't want to really challenge traditional astrophysics and say this could be a black hole, how about this guy? I don't know what this guy is. Nobody knows. 2.6 solar masses, you notice when I was showing the equation of state, is at the high side of what the models can potentially predict. So even nuclear physicists are a bit challenged by this. Nuclear physicists are very happy to claim these as neutron stars. They're perfect for their models, but this is a bit of a challenge. Yes?
In terms of eliminating more models for the equation of state, are you more waiting on like the ideal neutron star merger, or maybe that already was 170817, or do you need to just accumulate a larger sample of mergers?
It's an excellent question. I want a light neutron star. If we can, send Santa Claus request or something like that, I want this because it's less compact, so more deformable. So if actually you see this guy, this is perfect because if it's a neutron star, you will see tidal effects for sure. If it's a black hole, you won't see tidal effects when you expect it to see it. You'll know it's a black hole. Like you cannot observe white dwarfs, by the way. So it's either a black hole or neutron star. It cannot be anything else. So something like this, 1 to 1.2 solar masses. This is what I want to see. This is my. And as for your questions of the gold plate events or more events, in reality, we'll probably keep getting more events around here. But what I want is this. I mean, I'm going to keep analyzing all these, but this is what I'm hoping for.
By the way, Gaia DR3 is extremely sensitive in this mass range. They'll release Gaia DR3, which will be in the summer, will release a ton of compact binaries. We saw a leak that they will have thousands of invisible dark binary companions, and they'll be in this range. So now is the time to think about critical tests because they'll be executable this summer.
Perfect. And at this low mass range,
and they'll be very sensitive there. Yeah, Gaia can do it.
So yeah, which is good because we are not. As the mass goes down, we're a gravity experiment. As the mass goes down, we lose sensitivity.
Could you give us an idea of the variation in the mass radius orbit, the contour, whatever, with spin? The question I'm really leading up to is, if you see black holes at really clearly different masses, say different radii for the same mass. At what is there a certain separation you just can't get based on the spin
Yeah.
for a set common? So wondering whether that would be a way to say, oh, well, there has to also be a black hole, because a black hole can have any mass.
That's right. So the spin effect on the radius is quite small. I would say under 0.5 kilometers. So it will look something like this.
Okay, so then that would be a way possibly to, by luck, discover that something.
We don't have the resolution to tell those two apart. And additionally, if you actually see this and try to attribute it to spins, you have to explain why this thing didn't spin down after millions of years in a binary. That's another thing you have to deal with. But what would be exciting is if you actually see this and then see an object here.
Exactly, that's what I was.
If you see an object that has upper limits, you'd call it a black hole. The radius is small. But if you see an object that doesn't have upper limits, but you just have something like this, that could be a phase transition. Because some of those models, you go up here, and then you hit the phase transition and jump to a different branch.
Mhm.
This would be sort of a smoking gun signature of a phase transition in the neutron star. Because remember, once it develops the quark core, it softens and it decreases in radius. You have a pressure drop and the radius decreases.
You're saying in principle, it could actually be found both places. I mean, either place. It's not like you have to give up this branch.
Oh,
if that
no,
branch
you do give
exists.
up this branch. If it
Okay.
happens,
In that, but there
You
could
might-
be new physics. Don't forget, I mean, once we're here, and if you're in NYU, yeah, it's also
I was
new
gonna say
physics,
dark
right?
matter.
Right, because if
Yeah.
there's condensed matter in the dark sector, I mean, there really could be new physics there. And so
And
you really
then-
could have different objects, because some could have,
Exactly. And then you could legitimately see this,
Yeah.
one object here and then one object here with some.
that would be the
amount.
most exciting
Most
outcome,
exciting,
because that
yeah.
would really suggest new physics.
Though if you have a phase transition, they could overlap, but for like a tiny bit.
Right.
If they're actually overlapping for long, then I don't know what normal nuclear physics phenomenon could do that.
Well, maybe people need to run, but that was just terrific. Thank you. so
Thank you
much.
very much.
Could be condensed matter objects in principle, but that isn't really ruled out.
I think that the primordial black holes. Or you think that you don't have.
It wouldn't have to be black
Some
holes,
other
they could
nugget-like
be
black
outside, they could be like higher world objects that are bigger than